Okay, day 3, we're going to begin with resonance, property of vibration that where one imposing a frequency on something causes something to vibrate at that specific frequency because they're in tune with one another. Okay, so we will start by using the PowerPoint presentation, which is this one. Share. Okay, let's go to the slideshow. And here we are. So basically, we're going to go over some part of the chapter 25, mainly that of series resonance. So first, to begin with, we're going to look at some sinusoidal waves, try to refresh our minds as to what sinusoidal waves are, how frequency and timing values correspond to the wave itself. And we're going to look at some graphed waves, some typical frequency waves, and then we're going to look at some mixed frequency waves, signals. A lot of this has to do with the capacitive and inductive reactance. So we'll look and see remember how the capacitive and inductive reactance change with a function of frequency. And then finally, we'll end up with a talk on resonance in a series circuit, just for today. Okay, so first, let's refresh our minds with the sinusoidal wave. As implied, this is a sine wave, that is, it basically follows the y equal a sine of x mathematical equation, where we start out at zero angle, and increase to a maximum, and start to decrease again at a half cycle. And the next half cycle, we keep on decreasing. We reach a turning point, which is a negative peak, and go back up, and we're back to where we were initially, one period away. That period is labeled T as the time required to complete one cycle. If you take the reciprocal of that, you get frequency. Okay, so the period and the frequency are inverses of one another. We also know about peak values, peak-to-peak values, and somewhere in between is an RMS value, okay? The effective value is 0.707 peak value, which stands for, it's basically how you can measure the energy, the power being used to create this. So next we look at a typical, very common 60 hertz frequency wave. Basically 60 hertz is what we get out of our wall socket. And if we take only a 10 volt peak voltage out of that, that's what we get. This sinusoidal function where we've got in time, where we measure time in milliseconds. So we're looking at the output of this from the wall, a 10 volt output, and how it varies in the first 100 milliseconds. 100 milliseconds is only a tenth of a second, so it's a lot of things going on in very short times. The period of which then is going to be from where it starts here at 0 and where it comes back to 0 is here, and we've determined that that's approximately 16.7 milliseconds, or t equals 0.0167, because it's the reciprocal of 60. Okay. So if we look at a higher frequency, now 400 hertz or 400 cycles per second current is often available in aircraft. I'm not sure if it's available in submarines, but in aircraft, definitely 400 hertz is what the AC signals are on an airplane. And you see at 400 hertz how quickly you get repetition. So each wave, we've got about 20 cycles of waves in 50 milliseconds pictured here. Okay. And so there's a lot that can occur in that time. So the time is in milliseconds, and because you have this changes, those are changes occur very, very fast times. So it's interesting to take a look at, and it's good to see if you can have at hand actually a frequency and timing table. So we can look at low frequency, middle frequency, and high frequency. Start the low frequency stage. We're looking at something in the 100 to 1,000 hertz, or in other words, 100 cycles per second to 1,000 cycles per second. And the period that goes along with each of those varies from the low end, which is 10 milliseconds, up to 1 millisecond for the 1 kilohertz frequency range. Okay, at 1,000 at 1 kilohertz, you get a period of 1 millisecond. So things could happen at 1 millisecond intervals. Okay, that's what can happen electronically. So, but we don't normally use. Yes, we use a lot of things at 1 kilohertz, but usually it's much higher than that. Okay, so let's look at the kilohertz frequency range, where we go from 10 kilohertz up to 800 kilohertz, and now the period is measured in microseconds, or 10 to the minus 6 seconds, or 1 millionth of a second. So at 100 microseconds is the period for a 10 kilohertz signal. If you get up to 800 kilohertz, which is fairly high frequency, you're down to 1 microsecond interval. 1 microsecond interval, that's something that happens every 10 to the minus 6 seconds. That's unbelievable. Okay, but that is the nature of our electronics. Then the next step is to go to higher frequency, megahertz frequency. The megahertz frequency we can start at 10 megahertz, go up to 800 megahertz. Okay, the period that corresponds to these frequency ranges is measured in nanoseconds, or 1 billionth of a second. Okay, 1 billionth of a second is a nanosecond. So at 100 nanoseconds, well, at 10 megahertz, the period is 100 nanoseconds. Okay, all the way down up to at 800 megahertz, the things occur at 1.25 billionths of a second time intervals. So in today's electronics, though, we are capable of having something operate in the gigahertz, which is even higher. A gigahertz frequency That's an extraordinary, very high frequency, very fast time rate. And so with such high speeds, we can actually do a number of items that seem to be being performed at the same time, but because we can't see down normally as human beings in the billionth of a second or less time, then it looks like it's all happening at the same time. Okay. So we can essentially do multitasking simultaneously and notice no change. Okay. Gigahertz, that's where we are today in the current technology. So what do they look like? What the waveforms look like is a picture of number of different low frequency waves. So we got long wavelengths, okay? Low frequency is a longer wavelength. Medium frequency gets shorter wavelength. And we get to the higher frequency, which is even shorter wavelength. So the wavelength and the frequencies are inverse to one another. The amplitude and the frequency corresponding to a wave are independent of each other. So, but as I just mentioned, the greater the frequency, the smaller the wavelength. But we can, amplitude of the signal may be decreased by shortening the signal period. In other words, if we shorten the signal period, we could reduce the amplitude because of the time factor involved to reach those peaks. Okay, but we get somewhat of a different waveform. Okay, and most important, we take signals. Okay, we want signals such as audio signals and whatever, and we want to transmit them. We transmit them to a receiver that's picked up and we hear it on a radio or a TV. There are two basic modes that are used. There's the amplitude modulation, AM, and there's a frequency modulation. What does that mean? Well, in order for us to send out a signal and carry it over very long distances, okay, we actually weld together the audio signal with a modulating signal, such as you see on the top, okay, to create what you see in a form, in the case of amplitude modulation, where the amplitudes actually follow that modulating signal. Or we do it FM-wise, which is frequency-wise, where the frequency variation follows that signal, as you can see up on top. And then the entire signal is sent out more efficiently because of that higher frequency or that higher signal. Okay, so we want to also consider what happens when, in many cases, we have mixed frequencies. All right, so let's look at, we start out with a 60 cycle 10 volt, okay, which is pictured right here, 10 volt peak, 60 cycle, let's say call this a voltage. And on that, we impose an additional signal. Up here on the upper left, we're imposing a lower frequency signal upon this 60 cycle signal. So we get little bumps in between the big bumps, okay? But they're spread pretty far apart. Or we can have a higher frequency signal imposed on this on the backs of the 60 cycle signal, in which case again we get smaller bips at shorter distances away. Okay, so the mixed signal can look like this, or can look like that, and it can look like many other ones that we can't show right now. So what does, okay, how do we come about figuring out what resonance means? Well, first of all, we need to recall how the capacitive and inductive reactance works. Okay, both are a function of frequency. As you can see, for the capacitive reactance, for example, Xc is inversely proportional to the frequency. And you can see that as you increase the frequency, you decrease Xc, or decreasing Xc allows more to pass through. Okay, you get a smaller Xc is like having a smaller resistor, so smaller resistor allows for higher current. All right, so higher current at lower, at higher frequencies. So this is the opposite of what happens in case you have an inductance, an inductive reactance. In case of an inductive reactance, okay, you notice that the curves go in the totally opposite direction. All right, if you're going back to it, you can see that they slope down from left to right for capacitive reactance, but for inductive reactance, they slope up. They go from low to high. So you get high resistance or high reactance at higher frequencies, and the lower reactance at lower frequencies for inductive. So they both are opposite one another. Okay, so that's basically, and everything is going to be based on the sensitivity of a capacitor or an inductor, a combination, to how what kind of signals we're going to get out of circuit. But first, we need to define what resonance is. And for mechanical system, it occurs when the frequency at which a force is periodically applied is equal to or nearly equal to one of the natural frequencies of the system on which it acts. And this causes the stuff to oscillate with larger amplitude because of this resonance factor. In other words, we'll send out a signal, a vibration, basically an oscillation, noise. It could be a sound. Could have, it's picked up by an object. Okay, that object picks up that frequency, and if it's a frequency that's a natural frequency for that object, then it resonates. So it basically picks up the frequency that's being sent out and likes to resonate at that same frequency. Okay, and so that's what we call resonance. All right, and resonance can actually, because of resonance, we can actually break something. Okay, because the amplitude of that frequency can build up and build up until it actually breaks the object. In case of an electric circuit, though, it exists whenever the inductive reactance and the capacitive reactance are equal to in magnitude each other. So in other words, Xc is equal to XL. This causes the electrical energy to oscillate between a magnetic field of the inductor and the electric field of the capacitor. So essentially what happens is you're charging one you're charging one and discharging the other. So one actually uh, oscillates to charge up the other, and and then the opposite occurs. So first, the uh, capacitor energizes the inductor, and then the inductor charges the capacitor, and this keeps going back and forth. It's like a seesaw effect. So in physics, though, resonance tendency of a system to vibrate with increasing amplitudes. Okay, so you can get increasing amplitudes at some frequencies of excitation. They are known basically as the resonant frequencies. So basically you start out with a fundamental frequency above which you have a number of harmonics that can also be stimulated. So an object can have a natural frequency, okay? And if you send a signal that has that natural frequency, then that object will pick up and start resonance, and it starts to vibrate in a specific mode of that, in the same, at the frequency of its natural frequency. It's kind of pretty neat, actually. So, okay, why does it happen, and when does it happen? Well, the resonance occurs because of the collapsing magnetic field of the inductor, which generates the electric current in its windings that charges the capacitor. And then the discharging of the capacitor provides an electric current that builds up the magnetic field in the inductor, and the process is then repeated. Okay, that's how it happens. And when does it happen? Well, series RLC circuit, meaning resistor, inductor, capacitor circuit, when the inductive and the capacitive reactance values are equal in magnitude, but because they're equal in magnitude and opposite in phase, okay, they cancel each other out because they're 180 degrees apart in phase. And what happens is there's a sharp minimum in impedance, which means they cancel out. So basically the net effect, net reactance is zero, which is equivalent to a zero resistance. So the impedance is actually a minimum, and that is what's used to be in a tuning application, that we can use in a tuning application. So how do we derive that electrical resonant frequency? Well, we go back to our two equations. Xc equals 1 over 2 pi fc, and xl is equal to 2 pi fl. So we let one equal the other, and we solve for the frequency. Okay, and the frequency, a specific frequency, these will be equal, and they will be equal whenever we get the square root of LC into 1, okay, gives us the frequency. So we evaluate 2 pi times the square root of L times C to give us the natural frequency, the resonant frequency. So let's put that to the test. Okay, we have here a series resonant circuit. So for today, we'll just do the series, we'll consider resonant series circuit, of which we know in advance that the natural frequency or the resonant frequency is going to be 1,000 kilohertz. Okay, that's where our resonance is. So we start out with a resistance of 10 ohms, an inductance, an inductor of 239 microhenries, and a capacitor of 106 picofarads. Okay, this combination, if you put it into, we're only interested L and C. Okay, if you put it into the equation, you get that the natural frequency is 100 kilohertz. So we're going to plot the output, okay, from across, well, let's go back. You can look at the output across either the inductor or the capacitor, okay? And we're going to change the input or the power to vary from low frequencies above to above the 100 kilohertz frequency to see what we get as an output from either the inductor or the capacitor or both. So to do that, we're going to use a spreadsheet. So first we put in that the inductance is equal to that much, okay? And the capacitance is in picofarads, which gives us that, okay? And we're going to look at a frequency range between, it looks like 600,000 up to 12 million or whatever. These are a frequency range. And based on those, then we look at, we look at the XL value and the XC value, okay? And as we get to the 100 kilohertz or 1,000 kilohertz, okay, we can see that XL and XC are equal, okay? So we also look at XL minus the difference in these two, either below 100,000 and above 100,000. From the, we need those differences to figure out what the impedance is, Z. You know, Z is going to be a function of the difference in these plus the resistor. So it's R squared minus the square root of R squared plus the difference of XL and XC squared to give us a Z. And from the Z, we know what the voltage is that's applied. We get a current, so we can look at the current. Knowing the current, that we can get the voltage across the inductor and a voltage across the capacitor. Okay, so here we go. Current is equal to voltage divided by impedance, and XL is equal to 2 pi FL. XC is 1 over 2 pi FC. And so we use, again, these values above and below the resonant frequency. And we expect to get a peak value. This is normally what's seen here, is we get a peak value in current, okay, where we're actually measuring everything relative to the natural frequency, FR, which will occur we established at 0 point. And then we have a frequency increase and a frequency decrease. Okay, so as we decrease in frequency, it slopes down. As we increase in frequency, it slopes down again on the opposite side. Another important parameter may be the angle, okay, call it the impedance angle, okay, phase angle between the inductance and the resistance, which is that dashed green curve there. So according to what we get from, first we look at the current data from the simulation that we just did, okay? We look at the series current, and we get just like the curve that we saw we were supposed to get. So this shows that there's a peak. So in the case of a series resonance circuit, we get a peak in the series current, okay? If we look at what XL and XC look like in frequency-wise, okay, we know that XL varies linearly, as we see here, from low frequency to high frequency, whereas the capacitive reactance varies asymptotically from high to low, from low frequencies to high frequencies. And it's at this point here where they're equal, that's where you get resonance. Okay, so basically, if you're operating at a frequency below resonance, okay, then you have a capacitive, basically a capacitive circuit. If you're operating above that resonant frequency, you're operating inductively. And that's all that shows. So we can show that simply from the thing that we just created, from that circuit that we just created. These are our spreadsheet values, okay, that shows that they cross right at the 100,000, at the 1,000 kilohertz range. Okay, so that's what that shows. And if we look at what happens at that frequency, at the resonant frequency, then we see that we've got the voltage for VL is the red. That's the voltage, how the voltage changes in one cycle of and one voltage across the inductor, and the voltage across the capacitor, as you can see, is totally opposite that of the inductor. So this guy cancels that guy. It's in net. So basically you've got a net zero happening here. So if we look at the actual voltages itself around the 1,000 kilohertz range, we notice that there's a little lump on the inductive voltage, okay, which is an increase in the inductive voltage, and that shows you that that's where we want to operate at, okay, because in that case, that'll give us an amplification of what's going on, of the input. So basically, this is a picture showing how we can output. Nevertheless, we still get 45,000 microvolts, okay, which is much higher than the 3,000 microvolts that we get across the resistor. So greater outputs from the reactive components is what we get in that around near the 1,000 hertz range, the resonant frequency. Okay, this all leads to our conclusions that resonance is a phenomenon that requires oscillatory variations expressed as sinusoidal waves. Oscillation is what's the important word. So oscillations alone are not resonance, okay? Let's make sure that we don't get that mixed up. Just because something oscillates does not mean it's in resonance, okay? But if something is in resonance, we do have oscillations to be present, okay? So the opposite is true, but the direct is not. And basically, it's a sharing of the energy between two devices that have a common natural frequency. And the other important thing is that resonance only starts when there's a stimulus. So you got to start the thing, and we call that a momentary ping. So we just give it a little sharp ping to it, and it starts to resonate if the resonant conditions are set up properly. So the significant in a series circuit, electrical AC circuits containing a resistor, inductor, and a capacitive component, they exhibit resonance at a specific AC frequency when the reactances are equal to one another. And that reactance, that frequency, resonant frequency is calculated from that equation here. Resonant causes a series circuit current to peaks. We see that the current peaks as a resonant frequency. And then we can use that to select to create a specific signal frequency output from a circuit. So we can actually set this up so that we can create an output of a specific frequency. Okay, and that specific frequency will be FR, depending on the value of the inductor and the capacitor. And the output that we're going to be using then is going to be across one of the reactive components. Okay. So we're back, and tomorrow we will go look at what happens when you have a parallel circuit. But today we just studied what happens in a series circuit. And if you wanted to repeat this, you can repeat it directly from the PowerPoint presentation. Okay.